Hello everyone, I'm Brett Mulligan. I'll be talking about fuzzing open source Internet of Things projects. Here's a brief overview. I'll go over motivations, methods that I used, some results, lessons learned, and conclusions I think I can draw. So Internet of Things is still on the rise. By one estimate, there will be 75 billion Internet of Things connected devices by 2025. That includes phones, mesh networks, and sensor networks, but also home automation is big with Internet of Things, and then drone swarms or fleets of vehicles, and then as we saw with Mirai, Internet of Things can be a popular botnet target. So all good reasons to study Internet of Things security. I'll be looking at MQTT specifically. It's one of the most common IoT protocols. It stands for Message Queuing Telemetry Transport, and it's designed for low bandwidth, low power, and bad connectivity environment. It uses a subscriber and a publisher model. Down here you can see kind of the breakdown of how MQTT works. The backbone is the broker. Clients can be subscribers or publishers, and in this case the example is pretty typical. It's a temperature sensor, so it's a publisher. It sends it to the broker, this data at a given, could be based on an event or at a given time, and then the subscriber gets updated from the broker if it's subscribed to a certain topic, in this case temperature. So software under test in our case will be a MQTT client publisher. So the reason I went into fuzzing for this project is that it has it's a technique for finding vulnerabilities in software applications by sending it unexpected input or malformed input, and has been used in the real world to find actual vulnerabilities. Specifically, American Fuzzy Lop is one of the highest performing fuzzing programs. They've found real vulnerabilities in multiple products. So I'm using that as the backbone. And the target I selected was the Eclipse Foundation's Paho MQTT Library, available on GitHub. So my methods were to use AFL-Fuzz in the gray box configuration, which means the software under test has been compiled using AFL, so its code has been instrumented so it can see which branches it's taking and what the statement coverage is, and use that to make its fuzzing more intelligent. It's also able to use a black box or dumb mode, and then I use also a program called Radamsa to mutate inputs and make more inputs for AFL-Fuzz to use. I used a HTML file, a text file, a PNG graphic, a PDF, and Radamsa mutations as inputs. And then part of my setup was using Mosquito as the MQTT broker. And then monitoring the outputs. Just like you see on the right side, the top portion is the subscriber portion of MQTT. So it's seeing what has been published by the publisher. And you can see that AFL is mutating those inputs. And then this is what AFL looks like as it's running. It shows you runtime, the unique crashes and hangs, how fast it's going, and then the strategies that it's using. So part of AFL's setup was just the quick start from their website. That was fairly simple. They have good documentation. And then I configured the rest of it on Ubuntu. There was a specific change I had to make based on how Ubuntu treats core dumps, because that's one thing AFL is looking at. And then I had to instrument the Paho library by compiling it with AFL's compiler instead of the normal GCC. And then you can see the command down here to actually start the fuzzer is pretty long, so I just put that in a couple different scripts with different options just to make it easier to run multiple tests instead of typing that out every time. And then I also took advantage of some of the parallel operation that AFL is capable of to improve performance. and then monitored and interpreted the results as far as I could towards the end. So to start the fuzzer, I'll just go through some of the details down here. You start the program and then you give it the timeout value. It defaults to 1,000, so you don't have to put that in, but I was having too many timeouts early on, I think because MQTT is operating over the network and it's not super fast, at least on the hardware I was using. You give it also the input folder, and it goes through and looks at all those inputs and starts mutating them as it finds interesting results, and then it puts all those in the findings folder. And then under output, this is the software that I was testing that had been compiled using AFL, and then we're just telling it to use a test topic and to use the file that AFL is generating as the payload. So that's what that part at the end means. So for parallel operation, by design AFL only uses one core per instance. So on the box that I was using, I had 2 cores available, so I used a master and a secondary. I just call them Fuzzer 1, Fuzzer 2, and you just add those options in, and it basically doubled the throughput because they're not too reliant on each other. They're just kind of working in parallel. So as far as interpretation of the data, you can monitor AFL on its status screen as it's operating, or you can also use AFL plot to see its progress. There's an example here on the right, and then you can check hangs and crashes while it's operating, or at the end when it's complete. Just to go over this example, you can see over the multiple days it was operating that you can see cumulative total paths that it has explored, and then that there were no crashes, and that hangs kind of went up here just past 20, almost to 25, and it also shows you the executions per second, and the performance we're hanging out around 1.5, which again is pretty slow as far as fuzzing goes. But for Fuzzer 1 and Fuzzer 2, there are 17 and 19 unique hangs in this particular run, and I think that should be generalized over the number of executions so that you remove performance as one of the variables. So that's why I kind of use that metric. So a handful of those generated inputs caused hangs as kind of my major results. The execution, as far as AFL is concerned, a timeout is the execution longer than the given timeout value, which I use 1300 milliseconds to 1800 milliseconds. But I found out as I was digging into the specification of MQTT that these were valid executions of the protocol, because whenever it sees a null character, it is supposed to drop the connection. So in the end, I found no definite vulnerabilities yet, and I just need to verify that the rest of the inputs that caused hangs are due to null characters. This is the output that you get under the file fuzzer stats when you're completed or when you've completed a run of fuzzing. You can also check it while it's running. So you can see here that there were 19 unique hangs on this one. So lessons learned, the big one is that fuzzing is very resource intensive. That's confirmed by some of the other researchers doing similar kind of research. And fuzzing network protocols just adds another layer of complexity and latency into the mix. So take advantage of parallel capabilities. In conclusion, fuzzing is not always going to find something, but in this case I think it does suggest that the target software has achieved kind of a baseline stability. That doesn't mean vulnerabilities aren't present, and I'd like to continue to use the same methods on more open source projects, and then possibly forward those interesting inputs to the developers, because they're the experts on their particular software. Here are my references, and if you have any questions, I'll follow up on Canvas and Teams and via email. Thank you.